Hello, this presentation is on Cellular Automata, 1952. This is found in the Pickover book on page 406. My name is Jonathan Seagrave, and this is for Math 420, History and Philosophy of Mathematics, for the fall 2019 semester at Mayville State University. I hope you enjoy it.
What are cellular automata? Cellular automata are a class of simple mathematical systems that can model a variety of physical processes with complex behaviors. The simplest cellular automata are one-dimensional rows of cells that can have only two states, on or off. Here's an example of a one-dimensional automata. The universe of this automata is a line of cells that iterates discretely, one step at a time. Each cell has only two possibilities. It's either black or it's white. I've shown this here in the way that two-dimensional automata are usually shown. That is, that you can only see one generation at a time. Each generation replaces the previous one on the screen. Here is another one with a different rule set. They look pretty similar. If this was all you had to go on, you might think that they were the same. For one-dimensional automata, it's traditional to display them one generation after the next on top of each other, so that later generations scroll down from earlier generations. In this way, we can see the evolution of the automata all at once. Here are zoomed out images of the two automata that we were just looking at. When you zoom out sufficiently, you can see that they express larger scale order. More complicated automata may have 2 dimensions, 3 dimensions, or more. There isn't a limit, really. They can have multiple states for each cell as well. Here's an animation of some 3-dimensional automata. Though the rules governing the creation of cellular automata are simple, the patterns they produce can be very complicated. Who invented or discovered cellular automata? Early work began with Stanislaw Ulam in the 1940s when he modeled the growth of crystals using a simple lattice. Ulam worked with John von Neumann, who was attempting to create a self-replicating machine. Von Neumann created the first cellular automata in the early 1950s. It was two-dimensional, and each cell could have one of 29 possible states. Von Neumann proved that patterns could make copies of themselves within the automata's universe. The most famous cellular automata was popularized in 1970 when Martin Gardner wrote about the game of life in his October Mathematical Games column. So, how does all this work? In a two-dimensional automata, each cell has 8 neighbors. 1, 2, 3, 4, 5, 6, 7, and 8. The rules of the life game are simple. Every living cell with 2 or 3 neighbors survives for the next generation. Each cell with more than 3 or less than 2 neighbors is removed in the next generation, as if from overpopulation or isolation. And an empty cell with exactly 3 neighbors is born into the next generation. Let's look at some examples. First, if you just have an isolated cell, in one generation it'll die. It doesn't have any neighbors, so it goes away. If you have 3 cells right next to each other, the cell above and the cell below that line each have 3 neighbors, so they'll be born. The cells on the end of the line each only have the center neighbor, 1 neighbor, so they'll go away. The middle cell here, well, it has 2 neighbors, so it survives. So after the next generation, it'll flip to be a vertical line rather than a horizontal line. And it flips back and forth forever. These have been called blinkers. Look, if you put 5 cells right in a row, it'll quickly generate into 4 blinkers. Here's a pattern that's called a glider. It reproduces itself every 4 generations, 2 squares diagonally from where it started. Patterns have even been found that spit out gliders. Here's one that spits out a glider every 30 generations and reproduces itself.
People regard it now as a sort of computer game, We actually played it with Go stones on Go boards.
What are some applications of cellular automata? Well, applications include the modeling of the spread of plants, the propagation of animals such as barnacles, the oscillation of chemical reactions, and the spread of forest fires. Here's one that uses a hexagonal two-dimensional automata where each cell can have a few different states to model forest fires spreading. Here's one that's similar to the Belousov-Zhabotinsky reaction, which is a pretty interesting chemical reaction. On the right we can see the actual reaction, and on the left you can see the cellular automata. What's next? Well, if you want to know more about cellular automata, there's a few places you can look. Wolfram.com has a really engaging demonstration page where you can flip through hundreds of cellular automata examples. John Walker, the founder of Autodesk, also maintains a really great website that has a bunch of cellular automata. Finally, have a look at the mathematical universe hypothesis. Proponents of digital physics have suggested that the universe itself is one giant cellular automata.